is calculated the size of the horizon, which goes as 3 CT or 2 CT, depending on matter radiation dominated or matter dominated universe. I think this one is matter dominated universe. It is radiation RT. And from there we discuss mainly one main problem is called the horizon problem of standard Big Bang cosmology. So what is the horizon problem? Who can tell a little bit? Have you guys read about it after I told? Yes?
Little bit.
So who will tell me what is the horizon problem? Anybody can tell, or more people, more than one people can tell. Whatever you remember, tell me. Who would like to speak? Yes? What is this related to? Horizon problem, we remember?
The CMB.
CMB?
How like the universe has expanded so fast that CMB is almost uniform everywhere.
CMB?
It's uniform everywhere.
It
corresponds to 2.7 K everywhere, but
okay. So how many of you is still confused about the horizon problem? You can give a thumbs up. Confused means thumbs up. You want me to tell it again because this is a very important concept. Anybody or rest of all of you who understood? Avinash is little confused. Anybody else? Jahan, Gauri, anybody else? Rest of the people? Confused. So, that is called confusion, okay? So, if you totally didn't get it, that is not confusion. You are halfway there, no? Yes. Yes. So, what is the confusion? You have any question, you can ask me. Otherwise, I will tell a little bit. You can ask me the question. What is the confusion? That is the problem, and the solution to that is that in the beginning we need. So I'll tell you what happens. Suppose in the beginning of universe you take a very small area, small volume, which are in causal contact. That means the photon inside, there are many photon, maybe many photon inside, they know each other, so they may have interacted with each other, so that means they may have similar temperature. Now this may be the case, and then what happens, the space inside this tiny dot, if it suddenly blows up exponentially blows up in all directions. Blows up. How come the exponential blows up can happen? If there is a initial dark energy kind of fluid. You remember, no? Only exponential expansion can happen when AT can only go into the exponential when there is dark energy, right? Yes?
Yes, sir.
But
Yes, sir.
this dark energy will be a new dark energy. We call it inflation. Okay, it is not the standard. It is in the beginning of inflation, the beginning of universe. So this lambda, I'm calling it lambda prime. Lambda prime is basically the energy of inflation, but very similar to dark energy, but much higher order. So maybe the lambda prime value, the energy of lambda prime will be say 10 to the power 60 times or even more than lambda actual cosmological constant, which is the late acceleration we have seen in recent time universe. But in beginning major, the acceleration what has happened, which is way more powerful than this lambda's cosmological constant, and you can see this lambda comes as the power of exponential. So if the value of lambda is much higher, the expansion will be also much faster because e to the power lambda t. Is that clear?
Yes.
Because your h square Hubble parameter is rho, basically approximately 8 pi g by 3. I'm not writing it. It's some 8 pi g by 3 rho. K and then for cosmological constant it was like a lambda constant. And then if you solve a dot by a square, that is basically your a square is equal to a constant, and if you solve, you'll find at is e to the power lambda t. But if this lambda is lambda prime is much higher, then you'll get e to the power lambda prime t. And this lambda prime is much higher than lambda. So universe will be going to infinity almost to all direction. Space will blow up in femtosecond or in 10 to the power minus 30 second. And suddenly this small universe will come as a big universe everywhere, and this much blows up will happen. So all this photon inside will spread. They're a very high density photon, they spread. Now say this time is say I'm saying telling say 10 to the power minus 9 second. For example, within 10 to the power minus 9 second, the universe become much bigger that the radius of this universe is much higher, r at the after the exponential, I'm just calling it as r, is much higher than light could travel in that 10 to the power minus 9 second. Because how much distance light could travel in 10 to the power minus 9 seconds? C times t. So this is the centimeter or whatever velocity of light, depending on that. This is very tiny because in 10 to the power minus 9 second, light can travel maybe a little bit, like this much distance. But now, so photon could also travel this much distance. But if space has in the underlying space has blown up to infinity, almost like this big. So this photon, for now take this photon here and take this photon here. The distance between these two photons is much higher than the time times distance which photon can travel in a normal universe. So this distance is much higher than the horizon size, because horizon size is how much is kind of CT. I have been telling you, approximately CT, C times T. So is it clear that now the distance between photon is much greater than the D horizon which we have spoken, which is basically kind of CT, 3 CT or 2 CT. Is it clear?
Yes, sir.
Yes, sir.
Yeah. So now, if this photon, now suppose this, we are now talking about this, say 0.3 million year later. So now onwards, inflation stops, but still universe starts expanding slower. Of course, not exponential. Now the universe become radiation dominated at the end of inflation. So it will again go as A will go as D to the power half. But the thing is, it has already come out of horizon in a much bigger size. So right now, this photon, or this photon, if you don't know about inflation, then you will talk that my universe is only nanosecond old, But how come this photon here and this photon here has same temperature? How come they can travel much bigger distance, 10 to the power 30 times bigger distance than CT? Because that breaks the special theory of relativities. Because if this has some temperature T and this has temperature T, that means they has been in causal contact. But if you don't know about inflation, you will say, how come they can travel so much distance? Because universe में time ही नहीं है, means only 10 to the power minus 9 second is there. So only a tiny distance photon can travel, say this much distance. But it has traveled this much. Why travel? Because unless you travel, how can you communicate the temperature or anything? So is it getting clear now?
Yes, sir.
So now that's why you need an initial, this exponential blow up of the space where, so basic idea is to solve this problem, space expansion rate or velocity has to be much greater than the velocity of light. Then only you can bring two particles much beyond their causal horizon, much beyond than CT distance. CT is basically a causal horizon because that much distance light can communicate with given the age of the university. So what happens is now it's clear. Now it's clear. So already inflation, the initial expansion, exponential expansion blows things up to infinity in all direction. Almost infinity. Actually, it goes, we know now, e to the power 60 times a at the end of inflation, end of inflation, meaning end of that first dark energy is e to the power 60 times at in the beginning. So you can see that huge distance universe travel, the space travel. So anything in the space spread out into a very big radius, whereas your size of horizon remains this small. That means observable universe. Is it clear that the particles are thrown much beyond the observable universe? Because observable universe is C times T. Means suppose there is a observer here, that time intelligent life. Now, life is not possible. For example, say photon can sense. Then it can only communicate a distance CT within their horizon. So that is the idea. So now CMB also like that. So you look at the CMB sky, and you see their horizon size is like this small 1 degree length. 1 degree. 1 degree length. That is the size of the horizon we can calculate at the age of 0.3 million year when CMB. So if you calculate C times T, so C times 0.3 million year, this belongs to a distance this much, which today we know what is this distance. This is called angular diameter distance. We'll come to that later. So if you divide this r, small r, divided by this angular diameter distance dA, then you get the theta. And that theta corresponds to 1 degree in the CMB sky. 1 degree. So only 1 degree patch of CMB photon sky should have same temperature. According to, if you don't know anything about inflation, because we don't know. When even 20 years back, we didn't know, 30 years back, that inflation has to happen. But when we didn't find the reason that why they are all in same temperature, then we say that then in the beginning of universe, some exponential blow up has happened. So that means this photon, they were all together in a small patch. But now they have come far apart, not because the photon has traveled or communicated, because the space underlying has traveled much faster than the speed of light. Is it clear now? Yes?
Yes.
Or if you have any question, you can ask. See, if you don't have this high speed expansion than space, suppose the universe expands like radiation dominated era. So then universe will expand how much? Universe will expand a maximum 3 CT. So then you will end up in a same problem, because the distance you see between the photon is much higher than 3 ct, the age of size of the horizon. The 1 degree is the 3 ct. This 3 ct is basically 1 degree. But you see at an angle 60 degree or 90 degree, or 90 degree or 180 degree, all of them are in a huge distance. They are all carrying the same temperature. Yes, question now. Time for question.
Sir,
Yeah.
the expansion rate should be greater than the velocity of light.
Yes.
So that doesn't violate special
No.
theory.
Special theory says anything in the space cannot move faster than the speed of light, but space itself can move faster than the speed of light. Okay.
Okay, so space is beyond special theory.
Space is beyond the things, because nobody sees the space. Okay. Space is emptiness. It does not have any substance. It does not. You cannot say that space is a particle. Okay.
So there is no restriction on what space can do.
No restriction.
Okay.
That's the whole idea. Okay. So this is a new thing you are learning. The space can move actually faster, much faster than the speed of light. In fact, that has happened in the beginning, and that is again happening now in the dark energy dominated universe. Okay. Space is going exponential at the edge of the universe. Okay. Good. Any more question? This is very important. So now you know. So now when we say that what is the actual thing about the universe, now we have this new diagram, which is like this. Today is cosmological constant. In between there is a radiation dominated, then matter dominated, and today we are here. Cosmological constant is dominating, and it is 70% of the energy of the cosmological constant is 70%. E of Cc, cosmological constant, omega Cc. I'll talk about it. It's called omega Cc, and then omega matter, which includes. We'll talk about that, both dark matter plus visible matter. Omega visible means galaxy. Total 30%. Out of that, dark matter is 26%, and visible matter is 4%. Whereas photon and neutrino, they are like 10 to the power minus 5, or 10 to the power minus 3%. Fraction is 10 to the power minus 5, so 10 to the power minus 3%. So it is almost negligible today. But as you know, as you go beyond matter radiation equality, then photon or the neutrino, the radiation becomes very much important. So this cosmic cake, what we write, that this is 70% dark energy, 26% dark matter, and 4% visible matter. Visible. This is only for today, means at present time of the universe. But if you go back in early time, then you will see at some point it is matter and radiation, half. That is called matter radiation equality. That time, dark energy density, you can see it's almost negligible, because this is in log scale, log rho I. So it will be much higher value of matter. This one is the radiation. This one is the matter. We have done it, so I'm going faster. So this time, you can see that dark energy is way less compared to matter and radiation. So if you see the universe, you will see that dark energy that time become, say, 10 to the power minus 4. So everybody takes their turn. Like in life also, no, somebody has good time, somebody has bad time, and we laugh at them, and then you will see you also go through bad time, they are rising up. So sometimes it is the time of dark energy, sometimes it is the time of radiation, sometimes in between here is the time for matter. So universe is also like that, given good amount of rise up for everybody, means matter ko diya, radiation got, cosmological constant got, and in the beginning, now we have another flat line like this, ... And that is called lambda prime. We call it inflation. So again, there was a vacuum kind of energy. We don't know what it is. That's why we give it a name called inflation. It sounds very easy, but absolutely that is a name of our ignorance. Nobody knows why universe, what is that energy which blows things up. Nobody knows what is the dark energy, why it blows it up. Nobody knows what is dark matter, what blows it up. Only the 4% of the universe we know, but still there is so much mystery because we know that if universe comes from this lambda prime inflation at the end, basically it was just a pure energy of inflation, lambda. And if energy creates particle, suppose it creates particle E minus, then it has to create an antiparticle called positron because the charge has to be balanced. So from energy, if you suppose for photon is a pure energy, if you create particle, you have to create E plus and E minus, particle and antiparticle in equal number. So in the beginning of the universe, the inflation creates all the particles what we see today and their antiparticle in equal number. But somehow all the antiparticles has vanished from the universe so that galaxy can form, so that again the stars can form. Otherwise, suppose Jahang is here and an anti-Jahang comes and suddenly Jahang vanish. Okay, like that. So life will never be stable if you don't throw the antiparticle out of the universe. So this is another big mystery of the present cosmology, that where does antiparticle go and how? So this is one mystery. Number two, dark energy. We know they exist from an accelerated expansion of the space, got Nobel Prize, but we don't know what it is. Similarly, dark matter, I'll come to that today, towards the end a little bit. Dark matter, 26%. Today we'll prove that they exist, but we don't know what is. And then there is another problem which is called neutrino. Neutrino, we have been talking that it is relativistic like photon. It has very less mass. But from solar neutrino oscillations, we know that neutrino has mass. So neutrino mass is not zero. But we all knew from our theory of particle physics that neutrino mass should be zero. So why it is not zero, it's again a mystery. So these four things are the biggest question of cosmology at present time. And they are all related to, see, this one related to 4% of the universe, this one related to 70% of the universe, this one related to 26%, and this one is related to the radiation domain, radiation of the universe, which is negligible now, neutrino and photon I just told, but it was not negligible in the early universe when universe was radiation dominated. Okay? So this is the whole idea, that these are so many unknown questions. So now I'll tell you another problem, problem number two of Big Bang cosmology. So the first problem is horizon problem. So now this problem 2 is called flatness problem. It is related to the value of k equals to 0. We told you that our universe is flat from observation. I'll now explain you observation. That this has a problem with the Friedman equation. Are you all listening? Yes?
Yes, sir.
Yes. So now this one is also a little bit interesting. For that, let us all write down the Friedman equation. Who will tell me the Friedman equation now? It should be memorized. Okay. Tell me. A dot A square equals to
8 pi g 3.
by 3 into rho total minus k by s square. K is the scale. K is the k term goes into the FRW metric. You all remember 1 minus kr square, the
Yes, sir.
temperature term. Yes. And then we have this another one, a double dot by a equation. But now let us play with this Friedman equation today. So we can write down this equation as k by a square is equal to 8 pi g by 3h square rho. This is basically h, you know that, minus 1 minus 1. So now, if k equals to 0 today, we know that, then what will be value k? If k equals to 0, then rho will be how much? You tell me. Huh?
3h square by 8 pi g.
3h square by 8 pi g. This is called critical energy density of rho energy. That means if k equals to 0, then universe's energy density actually has to be rho c 3h square by 8 by g. Otherwise, you will not have a k equals to 0, right? From this equation? Yes? And this is what we measure from CMB and other survey of cosmology. And at present time, we find rho c 0 means you can measure this value at present time, then it will become 3h naught square by 8 pi g. So this is the critical density today, and it matched with absolute accuracy of present observation. That means the k term is really, really small, which we know from observation. So this is an observation. This is an observation. And then we know that if it is true, then k is to be 0 today. So now I'm moving to the problem of cosmology. The problem is very interesting. I'll ask you a few questions and you will already know the problem. So the problem is we write down this term, the Friedman equation, in a little bit different way. So we write rho critical. So we can rearrange this equation. It becomes k by a square h square is equal to rho by rho critical minus 1. Can you do that? I just I'm rearranging this. Can you check it? So do it right now that it is possible to do that. And what is the rho critical? Just take your pen and paper and see if you can write down the equation like this: k by a square h square. Sorry. Are you all doing it? Hello?
Yes, sir.
Yes.
It is very easy. So I'm just taking, you see, take the Friedman equation, 3h square is equal to 8 pi g by rho. From there, define rho critical is this one. Rho critical, I am writing that downwards, is 3h square by 8 pi g. I have just proved it. Rho critical is this. So use this and find out the first Friedman equation. Once done, let me know.
Done, sir.
Done? Everybody able to do
Yes,
that?
Yes, sir.
Yes, sir.
Yes, sir? Okay, very nice. So now we'll go one step ahead. So this term, rho by rho critical, is defined as omega. This is a new definition. So now for here, for example, मान लो that k equals to 0. It might not be, but we know from observation k equals to 0. For flat universe, then rho by rho critical is equal to 1. And rho is the sum of all the matter plus radiation plus lambda. So then this equation, if k equals to 0, then it becomes omega matter plus omega radiation plus omega lambda is equal to 1. So is equal to 1. Is it clear? And omega matter is how much? Rho matter by rho critical. Omega radiation is rho radiation by rho critical. And rho matter, you know how it goes. Rho m0 by 1 by times 1 by a cube. Rho radiation goes as rho naught by 1 by a to the power 4. And rho lambda naught is equal to rho lambda. It does not change. Is that clear?
Yes, sir.
So now this one is a much simpler equation, because that's what I said. This one is today is 0.7. Because total is 1 and sorry, this one is 0.3 and this one is 0.7. So total is 1 and this one is almost negligible, say 10 to the minus 3. So that's why it doesn't matter. It will be some fraction, will change here, but more or less 0.3 is omega matter and 0.3. So out of omega matter, then tell me how much will be omega dark matter? Who can tell me today?
0.26.
0.26. Yes, because 26%. So total rho C is basically the total energy density. Rho critical is at present, because see, rho critical is rho minus. So rho is equal to rho critical today. So that's why it is the total energy density. So 0.26 and omega visible is 0.04. 0.04. So many times in cosmology, they don't use 70% or 26%. They use this normalized number by omega c. So this is another way of writing the Friedman equation. Omega matter plus omega radiation plus omega lambda is equal to 1 if k equals to 0. Is this clear?
Yes.
Yes, sir.
Yeah. So now this omega matter is 0.3 is today only. I am talking about today. So omega matter is basically omega m0 by a cube. You can see it because rho, if you put it by rho naught by a cube, it will be like that. And omega radiation is omega radiation 0 by a to the power 4. Like that you can write omega lambda. So omega m0 is 0.3, omega lambda 0 is 0.7. But as you go early time, so today you can see, no, A equals to 1, we know from cosmology, A equals to 1, A naught equals to 1 today, A naught, at present value. I should write it properly. A naught at present value is 1. So this will become 1. So omega is equal to omega naught at present time. So now you tell me, if I tell you that this is the pen, take pen and paper. If I tell you today omega m0 is 0.3 and omega radiation, as I told you, is very less. So it's 10 to the power minus, say, 4. Today means at present time A equals to 1. So find the value of A, M, R, E. Means what is the value of A when matter and radiation was equal? That means what is the value of A when omega matter was omega radiation? Find the value. Take pen and paper and do it now. It's very easy. I have given all the hints. Because I told you in the past, they will vary with scale factor A, both. Today, their value is this, but they vary differently with scale factor. One goes as a cube, one a to the power minus 3, another goes as a to the power minus 4. So when you get the answer, tell me, approximately. Everybody do it. These are the simple things, arithmetic, you should be able to do it.
Uh, 3.3 into 10 to the power minus 4.
Who is speaking?
Jahang.
Okay. Other people also tell me the answer, then I'll tell you.
Yes, sir. 3.33 into 10 power minus 1.
Other people, Shruti, other people, everybody finding it?
Yes, sir.
Huh? How do you do it? You know that, no? That omega m goes as omega m0 by a cube, and omega rad goes as omega rad 0 by a to the power 4. So omega matter by omega rad goes as, you can see, omega m0 by omega rad 0 times a comes to the top and a to the power 4 by a cube. So there is a factor of a. It's basically a to the power 4 by a cube because it's inversely proportional. Clear? So there will be a factor of a. So now you see, if today is the ratio I have given you, how much? And I ask this has to be 1. So then you will find what will be the value of a. Okay? Clear, everybody? Yes?
Yes.
Yes, sir.
Very simple. So it's approximately 3000. I because I didn't give you the exact number here. So it has to be 3000. Sorry, 1 by 3000. 1 by 3000, a value. So what the value, Jahan? What is the value you got?
3.3 into 10 to the power minus 4.
4. Okay. So what is the value of Z then? You all know the relation between A and Z. Who can tell me? Jahan, you don't tell. Some other people, those who are silent. What is the relation between scale factor and Z? The redshift. If you don't remember, huh? Good. Tell me. Z, 1 by Z plus 1, not Z plus 1. Yeah? Yes. So these things everybody should memorize. Otherwise, you know. So now, you tell me if A value is today this much, approximately, what is the value of Z at matter radiation equality, value of redshift? What is the Z MRE, matter radiation equality? Calculate, everybody.
Around 2,999.
So approximately around 3000. Yeah?
Yes, sir. Yes, sir.
The exact value we'll know it later, but I don't know. So is it clear for everybody? 3000? Yes?
Yes, sir.
Yes, very nice. Now do the homework again. Right now take your pen and paper. What is the Z value when dark energy and matter equal? Today you know what is the matter value. Omega m naught is 0.3 and omega dark energy is 0.7. Omega lambda 0 is 0.7. So now I want the value of Z, same way what you do, that when matter and dark energy was equal, that means the dark energy domination started. Find the value of Z. Got the question, everybody? Yes? Please do it. I have given you enough hint, you should be able to do it. You don't look into the whiteboard, you just do your calculation. I'm just doing something else.
0.75.
Other people, everybody should get an answer, then we'll find what is the value of Z. Everybody got it? Some value?
A is equal to 0.75.
Okay. So this is your homework. It will be approximately that value. So you are right. Those other people who have not got, you just do it at home and send me. Even if you have done it here, make it in homework and send me. Only 3 people are sending me homework. Other people are not. Please contact Shruti, Avinash, or Jahan. That what was the homework? Because I told you that I will not give you the exact pen and paper sheet homework. I'll tell you time to time, you have to be attentive and you write down the homework, solve it and send it to me. Because I will not grade it, but if you only do the homework, you will see in exam, you will be able to do it. Otherwise, it will be hard. The concepts are very tough, but the algebra is very easy. So in the exam, the questions will be more on concept, but for that, you have to do the homework. So I request all the other 2-3 people to contact these 3 people and get the homework done. Okay? Shall you all do that within next 5 days? Homework? Those who have not sent. And I'll keep giving new homework. So today already I have given one. That find out the matter dark energy equivalent. So now you can see that redshift 0.7, redshift 0.7. So you see, I'm talking about redshift. Redshift Z is equal to 0 means present time. Z is equal to around 0.7 is dark energy domination start. DED started. Now Z is equal to around 3000. The matter dominator started, means the formation of galaxy, all these things, structure formation, matter dominator. And before that, it was radiation. Higher Z means radiation. So all the way to 10 to the power, Z is equal to 10 to the power 40 or 50. So this is another way of saying the time. You can write the same thing for A. A equals to 1 today. Then A equals to how much? Then here A equals to, you just said around 10 to the minus 4. And in the beginning, when Z is equal to very high, say 10 to the power 60 or 50, then A will be around, 10 to the minus 60. So this is a 2 different way of telling how the universe time scale is moving. Now you can see, who can tell me that today is present time and when this, what billion years dark energy domination started? I have told it many times. Who can give me the answer? So total from here to here, or rather here to here, is 14 billion years. So you tell me, this is the present time. So how many billion years back the dark energy domination started? Approximately? Who can tell me? Years, I want to, and you are able to hear my question?
Yes, sir.
Anybody knows the answer?
Yes, sir.
How much? You don't need to calculate it. I have told it, then only you know it. So I told you the dark energy domination started when Earth was just formed, or like Sun was formed. It was like around 4 to 5 billion years old. So
Around 8 billion years. 8.
no, around 8 billion years is from the time, age of the universe. I'm talking about from how many billion years back from now. Okay. So you can actually see this is 0 time, and then this is CMB is how much? 0.3 million year. Then it's good. Then here it will be around 8 billion year. If you come back from the lower side, then it will be then today it is 14 billion year. Is it clear? Yes.
Yes, sir.
Okay. So is this number correct? The dark energy domination started around when universe was 8 billion years old, 7 or 8. I think that is your homework. Okay. So now you can see that the scale factor and the redshift or the time does not go linearly. So you go from redshift 0 to 0.7, it is already in between is 5 billion years approximately. So from redshift 0 to 0.7 is 5 billion years. So that means if you see the supernova observation which is 0.7 redshift away, that means you are looking at supernova which is 5 billion year old. So that's why in IIA you will see they will always say a star at 0.7 billion years, a star at redshift 0.7 means it's a very far object. You need a 5 billion light years back means huge distance. You need an extremely high quality telescope like your Hawaiian telescope or Hubble Space Telescope like that. So with normal telescope, with India's highest telescope, you can go only 0.1 or 0.05 at present. So 0.7 means is pretty back in time, 5 billion years. But Hubble Space Telescope has been giving you stars and the formation of galaxies from 5 billion years old back. So Z is equal to 0.7 is already pretty. But now next generation telescope like JEST or TMT, they will go up to redshift Z is equal to 10. That means you will see it is almost like 13 billion years back. So almost close to the age of the universe with optical. So Z is equal to 10 means it's a very powerful telescope which is looking the universe which was 13 or 13 billion years back. Okay, stars was just getting formed. So higher the redshift you go in telescope, that means further away you go and you need a high technology telescope. Is it clear now?
Yes, sir.
Okay. So now let us do some fun. So I'll again ask you to take pen and paper. So this one now you know. Here, so let me get. Just one second. Yeah. Where is that? So like that, what we are do, I was looking in a convention. So what people do like that, this equation, people sometimes write it like that. 1 equals to omega total minus k by s square h square. Now, if k equals to 0, then we know omega total is equal to 1. We have just said that omega matter is 0.3, omega dark energy is 0.7, like that. Now, we defined a new quantity, little bit like that. We call it omega k, where omega k is nothing but minus k by s square h square. So it's another way of saying that if there is a curvature energy density, we define like that, then suppose universe is not flat. We don't know yet. I mean, we don't know observationally, but theoretically it may be different, say in the beginning of the universe or something. We don't know. Or what maybe it is 0 but very close to 0. We don't know today. We know that it has to be almost less than 10 to the power minus 4, this value. So it is almost omega total is 1. But anyway, let's keep this term. So now you tell me, so if universe is flat, that means omega k is absolutely 0. If omega is not flat universe, then this plus this is 1. Okay. If universe is flat, then omega total is 1. That means this k term is absolutely 0. But now, say for example, we assume that maybe this k by a square term, this term, say it has a very tiny value in the beginning of time. Because that time universe was very much twisted. The space was turned and twisted, Big Bang time. So maybe k not 0. Who knows? So say it has a non-zero value in the beginning, k by s square a square. In fact, that's people also believe that it has a non-zero value. Now, can you tell me that in a radiation-dominated era, because universe entered radiation-dominated era, how this quantity, this k by omega, how this quantity omega k with the mod value is proportional to, is a function of scale factor a? Can you take pen and paper and do it now? So I have already tell you what is this k by a square a square. You just need to put h square of radiation and then tell me the form of how omega k goes in radiation dominated era. Are you doing it? Is it clear? Hello?
Can you repeat it again?
Because if you don't understand, you have to ask. Otherwise, I will become silent and you will also become silent. There is nothing called silence here, in the classroom. So you asked me why you were scared to ask. So I just told you that find out the form of this k by a square, means how omega of k varies as a function of scale factor in radiation dominated era. So omega k is basically constant by a square. You have to put just a square value of radiation dominated era. And you know it in radiation dominated era. I am asking you to do it again and again because these are the basic assumption, basic thing in cosmology.
So it will scale as a linearly proportional to it.
Other people, please do it, then we'll have answer. How does H goes in radiation dominated era as a function of scale factor? Write down the Friedman equation and only keep the radiation term. Not able to do it? This is the most easiest thing ever.
Is it like a square?
Yes. It goes as a square. Awesome. And in matter dominated era, so how to do it is very easy. H square is 8 pi g by 3 times rho. And rho radiation goes as rho naught by a to the power 4. This is a square. So if you put it here, is a square times a square. A square is 1 by a to the power 4. So 1 by a square remains, and that goes into the numerator and become a square. For matter dominated, this is 1 by a cube. So a square times 1 by a cube. So 1a will remain, and it will go like this. Is it clear now?
Yes,
So
sir.
omega k, suppose you start with a very tiny value, say in the beginning of universe, because today we know that omega k is less than 10 to the power minus 3 from CMB. So for example, let's take a value 10 to the power minus 5 omega k value in the beginning of the universe. Now this value will scale as a square. So it will go increase or decrease as universe expand. Omega k value will increase or decrease.
K value is 10 to the power minus 5, right?
Shuru mein, in the beginning, I start with this is the value in the beginning. Okay, let me take this.
So it will decrease, sir. It will decrease.
Because you just proved that it goes as a square.
Yes, sir.
So then a is increasing, no? Scale factor. Is it clear? See, these are the very important thing. Very simple but very important. So it goes as scale factor squared. So scale factor is increasing or decreasing? Tell me.
Increasing.
Increasing, because that's what we know. What about all other people?
Yes, sir.
Shruti, please say your voice. Shruti, Gauri, Priyanka, I never hear your voice. Yes, scale factor is increasing or decreasing in the
It's
universe?
increasing, sir. It's increasing, sir.
So that means if you start with a small value of omega k, it will become bigger or smaller as you wait more and more? From this equation.
It will increase.
It will increase. That's the thing. So if you start with a very tiny value in the beginning, 10 to the power minus 5 or something, because today we know omega k, today we know that it is less than 10 to the power minus 3. That much we know from experiment, CMB experiment. So let's say it's a very small value, early time. But then the problem is, we know that scale factor was 10 to the power minus 60 at the beginning of universe, and today it is almost up to the matter radiation, up to the radiation, when radiation dominated end, then scale factor is, you just only told today, 10 to the power minus 4, AMRE. So the scale factor changes almost 10 to the power 56 times bigger from beginning of universe till now. Then how much will be the omega k today at the end of matter radiation equality? So I am doing it this calculation from the beginning till matter radiation equality. This will go as a square, and this is 10 to the power minus 4 a. and today almost A equals to 1. This you can more or less take, it goes as A, matter dominated. So you start with 10 to the power minus 5, then you multiply by A square, so it will be 10 to the power 56 square. So it will be 10 to the power 112. It will go as A square. Then again it will go as A by another 10 cube from here to here. So it will be 10 to the power 115 times minus 5. That means 10 to the power 110, which will be completely ruled out by experiment today. Because we know today universe omega k is 10 to the power minus 3. That means in the beginning, how much has to be omega k in the beginning? Because it goes by 10 to the power 110 almost. So it has to be almost 10 to the power minus 115 or something like that. If you multiply it by 10 to the power 110, then only today you can get a number which is 10 to the power minus 5. Is it clear? Or how many of you confused? I'll tell it again. It's very simple arithmetic, but I tell you this, that today we know this omega k from experiment that it is 10 to the power minus 3 or minus 4, less than, we don't know what is. Now, I have just proved by you that told that this omega k value, the density in the curvature, which is we have defined as omega k plus omega total. This is like just with another term, like here we did. Omega total is the density in the matter, radiation and energy, dark energy, and plus omega k. Now, omega k is very peculiar. All other omega matter, omega radiation, they decrease with scale factor, but omega k increases with scale factor. That means if universe expand, the omega k value, the energy density in omega, energy curvature, like this term, actually increases. So, now we know that this A square term from the beginning of the universe till radiation dominated, and then multiply, then again it will go as A scale factor. This factor is around 10 to the power 100 minimum. So if you today has to be with a value of 10 to the power minus 5, that means you have to start with a value of 10 to the power minus 15, 115 or even less. Because then you will multiply it. It is in the beginning, multiply it by 10 to the power 110, and then you will get still 10 to the power minus 5, small value. Then you will say like, okay, I'm okay with the experiment. So you need a huge small value of curvature in the beginning of universe. Is it clear?
Yes.
Now it is getting clear. You have to read it again and again. I will send you note. That's why in cosmology class, if you without preparation, if you come, you will only see that mathematics is very easy. I'll just do 2AQ times 5 times 10, but the physics is very deep. In other part of astrophysics, you can later follow the mathematics and get the exam done. But here, the concepts are very, very crucial. Here, exam you will just need to do a class 10 mathematics, a cube, 1 by a cube, like that. But the concepts are very deep. So that's why you have to study it. Every day I speak, you have to go back, make your own notes. If you don't understand, you ask me. Otherwise, cosmology is is a subject which is most fascinating at present time, but it requires some kind of intuition and intelligence. Okay, just doing mathematics, you cannot do cosmology. You need to understand it. Is it clear? Yes. Yes.
Yes, sir.
Yes, sir.
Yes.
The question is now. The question is. This omega k, whatever be it is value, k by a square, it has to be 10 to the power minus 115 or even lesser than that, So who made so low value? Who made it? Because it's not easy to start with a number like that. Second, again, similar problem. Because you are dealing with number of 0.5, it is almost like going in a tea shop, and you have a 10 rupee notes, 10 rupees notes, and you give him, and tea cost, say, 7 rupees, and you get 10 minus 7, so 3 rupees back. But this problem is something else. You go to a tea shop with 10 rupees, and somebody says, sir, my tea cost 7.00000000000001 paisa, 1 rupee. Please give me back, please give me change. It is impossible for you to give change. So when you deal with day-to-day life, all your numbers are almost similar so that you can have a dealings. So universe was dealing like that, but suddenly one number came up like 0.0000000000. So who fine-tuned it? So that we know that today omega k has to be less than 10 to the minus. This problem, that why it is such a fine-tuned value in the beginning of universe, is called flatness problem. Flatness problem. Okay. Is it clear now? What is the problem? Yes? How
Yes,
come
sir.
you suddenly get a so small number? Then there has to be a mechanism. Otherwise, who chose it by hand? Even if God put it by hand, how does God find such a small number of omega k in the beginning? Yeah. So it is not easy. Suddenly, if you are dealing with the physical laws and you say like, okay, see, it is like this. Electron mass, 501 keV. Proton mass, 1 keV. They're still 10 to the power 3 or 10 to the power 4 order of magnitude different. That's why they sustain in creation. But suddenly, if I say like there is a particle whose mass is 10 to the power minus 100 electron volt, then suddenly you say like, how come a mass is so low? So then there must be a mechanism. So like that. So the mechanism to this problem is also solved by inflation. So I'll come to that, and that ends today's class. The thing is, till in previous calculation, I have used only radiation dominated era and matter dominated era. Or dark energy, you can also say dark energy, because dark energy is only 0.7 recent past. It does not change that much. So now I have not talked about this in the beginning of inflation for the previous calculation. Now, can you tell me how this k by a square, this omega k, goes when the universe is inflation dominated or dark energy lambda, in the beginning lambda? Tell me. Now you do it again. You know it.
One by a square.
Huh?
1 by a square.
Everybody else, how does it go as a function of a cube?
1 by a square.
1 by a square. Very nice. Why? Because this a square is constant in inflation. It's like a lambda. Rho lambda is basically lambda, constant. So 1 by a square. Now you tell me, I was just telling in the beginning, suppose you start with a value 10 to the minus 5, but there is an inflation where universe becomes 10 to the power 60 times higher in fraction of a second. So higher means A becomes 10 to the power 60 times A beginning. So A becomes 10 to the power 60 times. So now you know this omega k goes as how much? 1 by a square during inflation. Yes, omega k? Yes? So how much will be the value of omega k at the end of inflation, when the inflation stops in nanoseconds? It will be initial value of 10 to the power minus 5 times how much?
10 to the power minus 120.
10 to the power minus 120. Very nice, because 1 by a square, and a has become 10 to the power 60. So see, even if you start with a okay number, inflation makes it goes to a very small number. Then you are done. You already create a number at the age of inflation which is 10 to the power minus 125 or even smaller, because this 10 to the power 60 is the minimum. Inflation can actually do 10 to the power 70 or 10 to the power 80 in nanoseconds. So it will be then 1. Then you do your radiation dominated universe, increase it with a square, and then again you do increase a square, you multiply it by 10 to the power 110, still you remain a small number of 10 to the power minus 5 or less. So now you know you don't have to start with a small value. Inflation will make it a very small value, 10 to the power minus 125, and then even if you want to increase as a square or a, still you will be remaining very small at present time. So that's why this flatness problem is also solved by inflation. Because luckily, during inflation, it goes as 1 by a square, it decreases. So you create a very small number automatically. There is a mechanism now to create a small number. You don't have to put by hand 0, 0, 0, 0, 0, 0 by hand. You start with a small number 10 to the power 4, minus 4 or 1. Then you multiply it by 10 to the minus 120 because the universe will expand. Then you already getting 10 to the minus 120 at the end of inflation. And then you start what we did in the last slide. Is it clear? Yes?
Yes.
Yes, sir.
Yes, sir.
So that's why inflation was incorporated for these two solutions. One is horizon problem, another is flatness problem. Big Bang cosmology, without inflation, Big Bang cosmology cannot solve these two problems. That's why we need dark energy domination in the beginning with a very much higher scale. And that is the present understanding of the universe. But we don't know why inflation happens yet. Gravity wave will determine that, gravity wave experiment in future. Okay? Because that time you need quantum gravity. Because the universe is so small, you need quantum mechanics. And universe is so dense, you need gravity. And when gravity and quantum mechanics both comes, we know that it creates a lot of 1 by zeros. And that's why you need string theory to understand inflation. It is similar to black hole singularity, as we discussed. So this ends the today's class. So I really request you go back, read horizon problem and flatness problem, see movies of horizon problem and flatness problem from YouTube. Try to get it in your heart. Okay. Then only we can go into the next class. Okay. In next class, we'll be doing very fascinating thing. The fascinating thing is really fascinating. You will come to know, because if universe is really homogeneous, even if you apply gravity, can you create galaxy? Yes or no? Suppose you have a totally homogeneous system, then what will happen? At each point, the gravitational force will be
Equal.
equal, they will cancel. Even if you increase gravity, you can never produce galaxy. So you need some initial fluctuation in the density. Otherwise, it is impossible to create life and galaxy. Tomorrow's class, not tomorrow, Monday, we'll see that inflation not only solved this horizon problem and flatness problem. Using simple quantum mechanics, we will show that you will create a fluctuations, tiny fluctuations, which is 10 to the power minus 5, means 1 in 10 to the power 5, means the order of fluctuation is, so if your CMB is 2.7 Kelvin, the temperature fluctuation will be 10 to the power minus 5 times 2.7, so 0.00001 level fluctuations. And that is what inflation predicts, that there will be a 10 to the power minus 5 level. So if you find the density rho, then there will be a delta rho, which will be 10 to the power minus 5 order of the mean value of rho. And it is fascinating that fossil radiation from that million of years much early, when universe is so baby, we see actually that in the radiation that the fluctuation is 10 to the power minus 5. So that's why people started taking inflation. That means your origin is quantum mechanics. Your origin is not classical. Universe came from really small thing. And next class we'll do the simple quantum mechanics to do how to generate this fluctuation. And then what happens to that fluctuation? tiny density, how they grow bigger and bigger and become galaxy. And that has already been solved, and we put it in supercomputer, and we create our galaxy starting from t equals to minus 10 to the power minus 9 second. So that is a fascinating thing in cosmology, that you can generate the billions of galaxies, and this tomorrow next class will show you simulation after calculating the quantum mechanics of inflation. But please read in the weekend this concept. So will we all read it? Yes? Yes? Yes, horizon problem, flatness problem, and give me a thumbs up that you will read it. And what we did before that, mainly these two problems, if you understand, then it will be away. And then the what is horizon? Okay, we show that how things enters inside horizon and how things go outside horizon. In radiation and matter dominated universe, things were entering horizon, and then in dark energy they started going out. And if we wait for another 4 billion years, we'll see everything will go out. Understand it, because I did simple mathematics, but I explained it. Okay? Good. So we'll see you on Monday. Okay?
Thank you, sir.